Hello everyone. This video is about energy and energy forms. We'll talk about the definition of energy, the different types of energy, and how energy converts from one form to another while it's still conserved, or the total energy of the universe is still conserved. In the previous lesson we talked about work, and we said that the reason we start with work because energy is defined as the ability to do work. So anything that has the ability to do work, meaning anything that has the ability to apply force and move other objects a certain distance, we say that this object has energy. Work and energy share also the same unit, which is joules. Now there are two types of energy. There is the kinetic energy and there is potential energy. Kinetic energy is energy due to the motion. Why do objects in motion have energy? Because whenever they hit another object, they will be able to perform work on that object, meaning they will be able to apply force and move that object distance. So a car moving has kinetic energy because it has the ability to do work. If this car hit a box in the street, it will be able to apply force on it and move it a distance, which is performing work. The other type of energy is called potential energy, and this is energy stored in the object due to its position or internal makeup. And we'll talk about those two types of energy in details. Kinetic energy can be divided into four major categories. There is the thermal energy, which is due to the motion that results from heating object. When you heat an object, the molecules inside this object will start moving faster and faster. The higher the temperature of the object, the faster its molecules will move. To see an example here, when you place water on a hot plate and start increasing the temperature and start increasing the heat, what will happen? The internal molecules of the water will start moving faster until eventually they have enough kinetic energy to flee the water surface and turn into steam. That's what we call it boiling. And thermal kinetic energy is not only limited to liquids or gases, it also includes solids. If you took a brick and subject it to heat, and let's look at the inside of the brick here, this shows the energy here. Notice here, whenever it's cold, the internal energy is small. When you start heating it, it will start gaining energy, and this energy will cause the molecules of the brick to move faster, and as a result part of the heat will be transferred to the surrounding, meaning that the atmosphere around the brick will start gaining heat from the brick, and the atmosphere around the brick will start gaining temperature. Okay, so that was the first type of kinetic energy. It's the thermal energy due to heating objects that cause the molecules inside that object to move faster. The second type of kinetic energy is the mechanical energy, mechanical kinetic energy, which we are all familiar with. It's the movement of a thrown baseball, moving vehicles, and so on. And this mechanical kinetic energy can be quantified in the form of an equation. The equation states that the mechanical kinetic energy is directly proportional to the mass, meaning the bigger the mass, the bigger the kinetic energy, which implies that it can perform more work. So if you have a small scooter versus a big truck, and if they are both moving with the same velocity and they hit the same object, which one will do more work on that object? Even though they are moving with the same velocity, the one with the bigger mass will be able to do more work, meaning it will apply more force on that object and move it further distance. And remember, work is force times distance. So the bigger the mass, the more work is performed, and hence the higher the energy of that object. So mass is the first factor. The second factor is the velocity, and the velocity is squared, meaning its effect is even more. So the bigger the velocity, the bigger the kinetic energy. And actually, because of the square, if you double the velocity of an object, the kinetic energy will increase by 2 square, meaning it will quadruple, it will increase 4 times. Another example, if you triple the velocity of an object, let's say you are driving your car and you are going from 20 miles per hour to 60 miles per hour, that's triple the velocity, the kinetic energy will increase by how much? It will increase by 3 times square, meaning it will increase 9 times because of the square here. So whatever you do to the velocity, the square of it will be multiplied by the kinetic energy. So the equation here is the kinetic energy is equal 1/2 the mass times the velocity square of the object. The third type of kinetic energy is called electrical energy, and this is energy due to the motion of electrons, electric charges. Electrons are the negative electric charges in the atoms. When electricity is conducted, electrons will move from the negative to the positive, and during this motion it has the ability to do work. We know that electricity can operate different home appliances and devices, so the motion of those electrons perform work. The final type of kinetic energy is the electromagnetic radiation, and the electromagnetic radiation actually is light, all type of light, visible light, infrared, ultraviolet, X-ray, gamma rays, microwaves, radio waves. All those are type of electromagnetic radiation, and we know that light has the ability to do work. We see that clearly in photovoltaic cells, solar cells, where the light hits those cells and knock out electrons out of them, knock out the electric charges and produce electricity. So light has the ability to do work due to the motion of the photons, which are the energy nature of light. So this was the kinetic energy that is divided into 4 types: thermal, mechanical, electrical, and electromagnetic. Now let's talk about the potential energy, and that's energy stored in the object, and whenever it's liberated it will perform work. The first type of potential energy is called gravitational potential energy, and this is energy stored in elevated masses. When you elevate an object, you are storing potential energy, gravitational potential energy in that object. Therefore, whenever you release it, it will have the ability to perform work. So for example, dammed up water that are used to generate electricity, when you elevate that body of water, you are storing potential energy in it. As soon as you release it, it will be able to perform work. As the case here with this faucet, if you open it, you see the elevated water that comes out of this faucet will be able to perform work. Will be able to rotate this turbine, apply force on it, and move it distance, so it will be able to perform work. This is basically elevated water. Whenever you release it, gravitational potential energy stored in it will turn into work. Now, can we quantify this gravitational potential energy? The answer is yes. We can put it in the form of equation. The bigger the weight of the object elevated, the more potential energy it has. So the bigger the quantity of water elevated, the more work you can get out of it. So weight is one factor, directly proportional to the gravitational potential energy. The second factor is the height, how far you elevate it, how high you elevate it. So the higher the object is elevated, the more gravitational potential energy it has, and hence it can perform more work. So gravitational potential energy will depend on the weight and the height. It's weight times height. Remember, weight is mass in kilogram times acceleration due to gravity in meter per second square. The second type of potential energy is chemical potential energy, and that's energy stored in the molecular structure of the material, whether it's combustible material like gasoline, coal, natural gas, wood, or it's type of food that can provide living things with energy, with ATP, that enable them to perform their daily work. So when the gasoline undergoes combustion inside the engine of your car, the energy stored in the chemical bonds within the gasoline will be liberated, and hence it can perform work. It can push your car, apply force on it, and move it distance. So when you step on the gas while driving, you are burning more fuel, more gasoline, and this combustion will liberate the energy inside the gasoline and push your car forward. The same thing with food. When you digest your food, you are liberating the chemical bonds within the food molecules, and it turns into energy that will give you the ability to perform work. So that's the chemical potential energy, which is energy stored in the chemical bonding, in the molecular structure of chemicals. And nuclear potential energy, on the other hand, is also energy stored, but it's stored in the nuclear structure of fissionable and fusionable nuclei. There is energy stored in fissionable materials such as uranium and polonium. When the nucleus of uranium-235 undergoes fission, it will liberate this energy. For example, if it was hit by a neutron, like we see in this animation, it will split into smaller nuclei, and part of the energy will be liberated, and this energy will have the ability to do work. The same thing for fusionable materials such as hydrogen. Fusion is opposite to fission. In the case of fusion, two smaller nuclei will merge, will fuse, forming a bigger nucleus, and in the process energy is liberated due to some of the mass converting into energy. And this is what happened inside the sun. Fusion actually takes place inside the sun, where hydrogen will fuse, forming helium, and in the process they liberate part of the energy stored in the nuclei of hydrogen. So that was an introduction to the two types of energy, kinetic and potential, and the multiple subcategories within each of those major categories. Now, how about conservation of energy? Conservation of energy means that energy is neither destroyed nor created. It can only change from one form to another. So the total energy at time 1 will be exactly equal to the total energy at time 2. And here we are talking about the total energy of the universe. A good example is the simple pendulum that we saw in the lab. When you have a simple pendulum and you shift it up to a certain height, h, it has zero velocity. At the moment it's released, it has zero velocity, while it has maximum height. Now remember, is the weight times the height, so it will be all potential energy, while the mechanical kinetic energy will be zero. Now as soon as you release it, the height will start decreasing, meaning the potential energy will start decreasing, while the speed of the pendulum will start increasing, meaning the kinetic energy will be increasing. Remember that the potential energy is the weight times the height, and the height here is maximum. This is the gravitational potential energy, while the mechanical kinetic energy is equal to what? Is equal to 1/2 the mass times the velocity square, and here the velocity is zero, so the mechanical kinetic energy is zero as well. Now whenever it's released, it will start gaining speed, and hence part of the potential energy will convert to kinetic energy. The height is less now, while the pendulum is moving faster, and so on. It will continue gaining speed and losing height. At the bottom of the swing, it will be all kinetic energy because the height is zero while the speed is maximum. So all the potential energy has converted to kinetic. Then start elevating again, gaining height, and hence the kinetic energy will now turn into potential energy until it reaches its maximum height at the other side of the swing, and so on. It will continue alternating between potential and kinetic. Let's see this animation here. As you see in this animation, the pendulum will start with maximum height, it's all potential energy. While it's falling down, its potential energy is converting to kinetic, back to potential, and now kinetic energy. Ke is kinetic energy, P is potential energy, and so on, going back and forth between gravitational potential energy and mechanical kinetic energy. Of course, air resistance will eventually change all the energy to thermal energy. So eventually we lose the gravitational potential energy and the mechanical kinetic energy to thermal kinetic energy due to the air resistance and the heat generated by the air resistance. Another example is a ball rolling down an incline like the one we saw in one of the experiments. Initially, the ball is at its maximum height, the speed is zero, so all the energy is gravitational potential energy. Whenever the ball is released, it starts losing height while gaining speed, hence its kinetic energy will be increasing since the speed is increasing, and the potential energy will be decreasing because the height is decreasing until it reaches minimum height at the bottom of the incline. At that point, all the energy would have been converted to mechanical kinetic energy. Then if you have another incline beside the first one, it will start rising up until it reaches the same height if there is no friction, and it's back to all potential energy, and so on. It will continue rolling back and forth, reaching the same height, assuming there is no friction. Now, if there is friction, which is the case in the real world, there is always friction, it will lose all the energy to heat, and heat is thermal kinetic energy. So notice here when we talk about lose the energy, we're not talking about destroying energy, we are talking about energy changing form. So the energy will change from gravitational potential energy and mechanical kinetic energy into heat, which is thermal kinetic energy due to friction. A very good example is conversion of energy inside your car engine. Initially, the energy comes from the gasoline. The gasoline has chemical potential energy. Whenever you start your car and you step on the gas, this chemical potential energy will be converted to thermal kinetic energy when the gasoline is combusted. This thermal kinetic energy that manifests itself in the movement of the gases produced by the combustion will push against the pistons inside the engine cylinders, converting this thermal kinetic energy into mechanical kinetic energy by the movement of those pistons that transfer to the tires and hence propel the vehicle. Unfortunately, 75% of this energy that results from the combustion of the gasoline will be lost to the environment in the form of wasted thermal energy through the exhaust and the radiator of your car. That's why after you drive your car, you'll notice that it will get hot, and that's why we have water in the radiator to cool it down. You are only using less than 25% of the energy of the gasoline to operate your car. That's why we said that everything eventually turns into thermal kinetic energy. This chart here shows you all the type of energy conversion. The source of all the energy in our planet comes from the sun, and the sun, as we learned, has nuclear potential energy due to the fusion of hydrogen forming helium. The nuclear potential energy will convert into electromagnetic radiation. That's the light that comes to us from the sun, and this electromagnetic radiation turns into chemical potential energy during the photosynthesis, where plants build their food. And of course, this chemical potential energy will convert to us as humans when we eat plants. It will convert to chemical potential energy for animals as well when they eat the plants. The same thing when we eat the animals, we are taking part of this chemical potential energy, and that enable us to do work. Also in heat engines, the electromagnetic radiation can be converted to mechanical kinetic energy. Also, due to friction, any mechanical kinetic energy will be converted to electromagnetic radiation, basically infrared. Any heat actually will turn into infrared radiation. Electrical kinetic energy will be converted to light in light bulbs, while in the solar cells the light will turn into electrical kinetic energy. Also, chemical potential energy stored in batteries can turn into electricity, electrical kinetic energy, and vice versa. Electrical kinetic energy can be converted to chemical potential energy during electrolysis and charging batteries, and so on. So this chart actually gives you all the conversions that take place between those types of potential and kinetic energies. But remember, in all those cases, the total energy will stay the same. It's only changing from one form to another. A good example of how we get energy as humans, as we mentioned, the energy from the sun that comes in the form of light will be used by plants during photosynthesis to make up food. The food has chemical potential energy. When we eat it, it will turn into mechanical kinetic energy that we can use it to do work. And when we do work, we are losing heat, and this heat will be in the form of IR, which is infrared. So basically, the light that comes from the sun will eventually be converted to light as well, because infrared is type of light. This table here, different units of energy. We know that the standard unit, the metric unit, is joules. And here we'll see how joules is related to all those types of units. Calories is defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And calorie is equivalent to 4.18 joules. Notice here that calorie is different from food calorie. Actually, 1 food calorie is 1000 calories, meaning 1 food calorie is equivalent to 4180 joules. Okay, so don't confuse calorie with food calorie. BTU, or British Thermal Unit, is the energy needed to raise the temperature of 1 pound of water by 1 Fahrenheit, and it's equivalent to 1055 joules. It's a little bit more than 1 kilojoules. Kilowatt hour, which is the unit that the electric company uses to charge us, is equivalent to 3.6 times 10 to the power 6 joules. A natural gas unit, which is around 1000 cubic feet of methane, of natural gas, will produce around 1 billion joules, 10 to the power 9 joules. A barrel of oil, which contains 42 gallons of oil, will produce 5.8 times 10 to the power 9 joules. And that's right now actually it's around $45.5 per barrel. Coal, 1 ton of coal will produce 26 billion joules. So this is just to give you an idea how the different units of energy are related to joules. In the next video, we'll go over the problems. Thank you for watching.